In this section, we're going to look at gravitation. We're going to start by looking at Newton's law of gravitation. Newton's law of gravitation. This law states that any two objects in the universe attract each other with a forces proportional to the product of masses and inversely proportional to the square of the distance separating them. This law states that any two objects in the universe attract each other with a force proportional to the product of their masses, and inversely proportional to the square of the distance separating them, to the square of the distance separating their centers, Okay, so let's say we have these two objects. Let's say this is M1. Let's say this is M2. So this law basically says let's say the distance is also R. So this force, the gravitational force between these two forces, is proportional to the product of the masses and inversely proportional to the square of the distance separating them. Okay, and this can be changed to equality by introducing a constant proportionality. The constant proportionality is represented by capital G. So you've got this G, M1, M2, divided by the distance separating them. Okay, so G is called universal gravitational constant. And its value is 6.67 times 10 to the power of negative 11 Newton meter squared divided by kilogram squared. So this represents the magnitude of the force by which the two objects attract each other. Now let's look at the direction. The direction of the force is along the line joining their centers. The direction of the force is along the line joining their centers, and there are two possible directions. That direction can be determined from the fact that the force is attractive. For example, we're looking for the force exerted by M1 on M2. That is what M1 is doing to M2. It's an attractive force, so this would be the direction of the force. And if you're looking for the force exerted by M2 and M1, then the direction of the force would be this way. It's attractive. Okay. Now, if EF, this is a unit vector in the direction of the force, then we can write this we can write this formula in a vector form. Will be G m1 m2 divided by the distance squared in the direction of EF. Okay, if the default angle of the force is theta F, if the default angle or direction of the force is theta F, then we have EF equals cosine of theta F in the I direction plus sine theta F in the J direction. Okay, so we can write this force FG equals G m1 m2 divided by the distance squared, and then the unit vector, the direction of the force, which is cosine of theta F in the I direction plus sine theta F in the J direction. Okay, so this is a vector form of the force. All right, so this is the expression for the force in terms of the direction of the force. But also we can express this formula in terms of the position vector. Sometimes easier to look at the direction of the position vector than the direction of the force. Okay, so let's look at the formula in terms of position vector. Expressing this formula in terms of position vector, that is, we're going to use the direction of the position vector instead of the direction of the force. Okay, so suppose, let's say we're looking at these two objects. Let's say this is M1, this is M2. Okay, so let this one F21 be force exerted by 1 on 2. Okay, and let this position vector R21 be position vector of 2 with respect to 1, with respect to 1. Okay, so this is the position vector of 2 with respect to 1. Let's call that one R21. Okay, now the unit vector in the direction of this position vector, let's say this is ER21, this is position vector, unit vector in the direction of R21. Okay, so we're talking about this unit vector over here. Let's say this vector is E21, the unit vector in the direction of the position vector. That is, this vector over here is the position vector R21 divided by R21. Okay, now let's compare the direction of the force and direction position vector. Now we're looking at the force exerted by M1 and M2. So the direction of the force is opposite to this direction over here. This is the direction of EF. This is the direction of EF, the direction of the force, because the force is attractive. Okay, so we can say that this E21 is a negative of EF. Okay, so the direction of the force is a negative of the direction of the unit vector in the direction of the unit vector in the direction of the position vector. Okay, now let's go to the general formula. We're looking at the force exerted by on 2 by 1 equals G M1 M2 divided by R21 squared in the direction of the force. Okay, but this equals the negative ET1, so we can write this one as this force over here as G M1 m2 over r21 squared, and then we can replace it by the unit vector in the direction of the position vector. Okay, of course this equals, but this equals this position vector divided by its magnitude. So we have f21 equals g m1 m2 over r21 squared. We've got negative over here, and then we have r21 divided by r21. Okay, so we get the following formula in terms of position vector. So the force exerted by 2 on 1 in terms of position vector is m1 m2 over r21 cubed in the times the position vector r21. So this is the formula of the gravitational force in terms of position vector. So when we do this formula, all we have to find is the position vector of the object is being acted upon with respect to the object is acting. Okay, all right, so we're going to look at an example now. First we're going to look at one-dimensional example. We're going to have, let's say, these two particles over here. Let's say this is m1 equals maybe 10 to the power of 3 kilograms. Let's say this is m2 equals maybe 10 to the power of 4 kilograms. And let's say this distance over here is 1000 meters. Okay, so A, we're going to calculate the gravitational force, exerted by m1 on m2. Okay, now I'm going to do it using both the force formula and the position vector formula. Okay, so first let's using the EF formula, that is the position vector formula. So in that case we have the following for this one. This 2 on 1 equals g m1 m2 divided by the distance squared. Okay, and then the unit vector is the unit vector in the direction of the force. All right, so what do we have over here? G we know is 6.67 times 10 to the power negative 11. Our m1 is 10 to the power of 3 kilograms. Our m2 is 10 to the power of 4 kilograms. Our distance is 1000 meters. Now the unit vector, or let's say, we know that the force exerted by m1 and m2 is attraction, so it's going to be in this direction. Okay, so if you want, you can say it's trivial, but we can say theta f, the direction for this direction is 180. Okay, 180 degrees, and then we can say ef equals cosine of theta f in the I direction plus, this is trivial, it's negative I, but just to be technical about it, theta f in the j direction. Okay, so it will be cosine of 180 in the I direction plus sine of 180 degrees in the j direction. This one is 0, so negative 1, so you get negative I. Okay, so that's it. So this direction over here is negative I, and so you get the formula F, well, by 2 on 1. Let me get the other side. F exerted by 2 on 1 is G m1 m2 divided by r12 squared. This is the vector direction of the force. Okay, so you've got 6.67 times 10 to the power negative 11. Okay, and m1 is 10 to the power of 3, m4 m2 is 10 to the power of 4. The distance is 1000, that's 1000 squared, and then the unit vector is negative I. Okay, so from the numbers we get 6.67, and that'll be, this is 7, we get 6 over here, 10 to 6 0, so negative 17 plus a negative 10, so this times 10 to the power of negative 10 newtons in the negative I direction. Okay, so this is using the force formula, and next I'm going to do it using the position vector formula, just to contrast. Okay, using the position vector formula, using the position vector formula. Okay, the position vector formula is, you get this force equals the negative of g m1 m2 divided by r1 to the distance cubed, and then the position vector, this is 2 1, it's the same thing but r2 1. Okay, so you see in this formula all we have to identify is the position vector. All right, so the position vector is a vector whose tail is the object that's exerting the force and whose head is the force the object is being acted upon. Okay, so this is my position vector r2 1, position vector of 2 with respect to 1. So as you can see, this is 1000 meters in the I direction. Okay, so we have r2 1 is 1000 in the negative I direction, and of course the magnitude of this is 1000. All right, so with that we have the force that is negative 6.67 times 10 to the power negative 11, which is the same, and then times 10 to the power of 4. The distance is 1000, so it will be 1000 cubed like this, and then we have the position vector, which is 1000 in the direction, this is in the direction of I, I'm sorry, the direction of I, this is positive I. Okay, so we get just like this one, oh, this is just like that one, 6.67 times 10 to the power of negative 10 newtons in the negative I direction. Okay, so they're both equivalent, but sometimes it's easier to look at the position vector than it is at the force, so it might be easier to use this formula in some instance, this position vector formula. All right, now how about if I ask the force exerted by 2 and 1? Okay, let's say B, calculate the gravitational force exerted by M2 on M1. Okay, so previously we've been looking by the force exerted by this one on this one. Now we're looking at the force exerted by this one on this one. Okay, so these are action reaction forces. So in this case we're looking at F exerted on 1 by 2. Okay, that's what we're trying to find out. But you know, these two forces are action reaction forces. The force exerted on 2 by 1 and the force exerted on 1 by 2 are action reaction forces, are action reaction forces. Therefore they're negatives of each other. Therefore they are negatives of each other. Negatives of each other. Okay, so we have F12 is the negative of F21. Okay, but we already did F21. F21 is this in the negative I direction, so this is the negative of 6.67 times 10 to the power of negative 11 in the negative I direction, right? So it's basically 6.67 times 10 to the power of negative 11 in the I direction. Okay, so this object is pulling to the right, that's why in the I direction, and this object is pulling to the left, that's why it is in the negative I direction. All right, now we're going to look at the superposition principle. Superposition principle. Superposition principle. How about if an object is in the vicinity of a number of objects? Well, all it is, you calculate the gravitational force due to each object and they add them vectorially, okay? If an object is in the vicinity of a number of objects, the net gravitational force acting on the object is the vector sum of all of the forces exerted by the other objects, okay? So let's say we have this object, let's say it's m0, and then you've got a number of objects over here, m1, let's say m2, m3, and so on, and these distances are let's say r01, r02, r03, and so on. So the net gravitational force will be the sum of the gravitational force exerted by each object, okay? So the net force exerted on the mass object, let's say this is the net, would be the sum of the force exerted by 1 on 0, the force exerted on 0 by 2, the force exerted by 0 by 3, and if there are more, the same pattern continues, okay? So you just obtain the net force exerted, the force exerted by each object, and then you add them together, okay? So this would be negative g m0 m1 divided by r0 1 cubed in the direction of the position vector r0 1, and then minus g m0 m2 divided by r0 2 cubed, and then you've got the position vector r0 2, and then, well, the same pattern continues, okay? So we can factor out this gravitational constant and m0, so this would be, so we can write this f net force exerted on m0 is negative g, we can factor out m0 too, okay? So you've got m1 r0 1 divided by r1 cubed plus m2 r0 2 divided by r0 2 cubed, and so on. So the same pattern continues, okay? So you simply add the gravitational force exerted by each object to get the net force acting on the object, all right? Okay. Well, we can write this one if you want. The net force and m0 equals the negative g m0, and then we can sum this over I. We can write this as mi r0 I divided by r0 I cubed. This would be the short way of writing it. Okay, so we're going to look at an example. Suppose we have the following situation. Let's say we have the following coordinate system over here. Let's say we have a mass of let's say this is m1. Let's say m1 is 1000 kilograms. Let's say this distance over here is maybe 3000 meters. This distance over here is 3,000 meters. 3,000 meters. Let's say we have another object over here. Let's say it's M2 equals 2,000 kilograms, and let's say this distance over here is 3,000 meters. And then we have another object over here. This is the object we're trying to calculate the force acting upon it. Let's say this is 4,000 meters, and let's say this is m naught equals, let's say 3,000 meters. Okay, so the question is calculate the net gravitational force acting on m naught. Okay, so we've got two objects acting on this one. So the formula would be this net gravitational force acting on mass m naught is negative g times the mass of m naught, and then you've got m1 r naught 1 divided by r naught 1 cubed, and then plus m2 r naught 2 divided by r naught 2 cubed. Okay, that's what we have to calculate. So we have the masses. This mass m naught is 3,000 kilograms. M1, this mass over here, is 1,000 kilograms. We have M2, which is 2,000 kilograms. Now we need the position vectors. So this is the position vector of M0 with respect to M1. Okay, that is the position vector whose tail is at M1 and whose head is at M2. We're talking about this position vector over here. This is R naught 1. Okay, so as you can see, it is 3,000 in the negative direction plus 4,000 in the I direction. So R naught 1 is 4,000 in the I direction minus 3,000 in the J direction. How about the magnitude? The magnitude of this one is square root of 4,000 squared plus 3,000 squared, okay, which is 5,000. All right, and we do the same thing for R naught 2. This position vector of this one with respect to this particle. So this is our position vector. This is R naught 2. Okay, so as you can see, this vector is, you see, it's going up. That's 3,000 in the J direction plus 4,000 in the I direction. Okay, so R naught 2 is 4,000 in the I direction plus 3,000 in the J direction, and the magnitude of the position vector is the square root of 4,000 squared plus 3,000 squared, which is 5,000 meters. So we have everything we need to calculate this. All right, so we have F net equals the negative of G, that's 6.7 times 10 to the power of negative 11 times m naught, the mass of the object is being acted upon, is 3,000 meters. Then we multiply this by m1 is 1,000 kilograms, so you've got 1,000 divided by 5,000 cubed. The distance is 5,000 for this one. Okay, 5,000 cubed. And then the position vector R naught 1 is 4,000 in the I minus 3,000 in the J. This is 4,000 in the I minus 3,000 in the J. Okay, and then the second one, M2 is 2,000 kilograms. and the distance is 5,000 cubed, and then the vector, the position vector is 4,000 in the I plus 3,000 in the J. Okay, we close the bracket. So basically after that it is simplification. Okay, so we can factor, let's factor this out. 6.67 times 10 to the power of negative 11, we got times 3,000. Okay, as you can see, we can factor out the 5,000 cubed, like this, and also there is a common of 1,000. You see, you've got 10 to the power of 6 from each of them. 1,000 times 1,000, so you've got 10 to the power of 6 too. We can factor the 10 to the power of 6, so we get from the first we get 4, or there's one over here, 4 in the I minus 3 in the J. Okay, and then from the second one, let me put a big bracket over here, and then for the second one we have 2 times 4 in the I plus 3 in the J. Okay, so we add the i's together and the j's together. Okay, so this constant over here is negative 6.67 divided by 125, and then you've got, well, this times 3 is over here, times 3 divided by 125, and then 10 to the power negative 11, we got 9 over here, 10 to the power negative 2, and then minus 10 to the power of 6, that'll be times 10 to the power of negative 2 minus 6, I guess negative 8. Okay, and then we add the i's together. That's 4i plus 8i. Okay, that's 12 in the I, and then minus 3j plus 6j is plus 3j. Okay, so this would be the force exerted by the two objects on the mass m0. All right, now let's look at you might wonder how they measure the mass of the Earth. So let's look at how they do it. So let's look at measuring the mass of the Earth. The mass of the Earth. Let's see how they do it. Okay. Suppose, let's say this is the Earth over here. Okay. So let's say, so this is the mass of Earth. All right. And let's say we have an object M over here. So let's look at the force exerted by these two objects. Let's call this distance between the center of Earth and this object R over here. So the gravitational force exerted by Earth on this object would be, this would be the force. The gravitational force is G, the mass of the object, the mass of Earth, divided by the distance squared. This is the gravitational force exerted by the object. Now suppose this is the radius of Earth and this is the altitude. So you've got R equals radius of Earth plus its altitude. So we can write this as G M E divided by the radius of Earth plus the altitude squared. Okay, now let's obtain expression for the gravitational acceleration due to this force. Okay, so we can also say this force over here equals mass times acceleration. Okay, so the acceleration is this force divided by mass. Okay, so if you apply that, we get acceleration equals, if you divide by mass, you get G, mass of Earth, divided by R plus H squared. Okay, now if the object in the surface of Earth, H equals 0. If the object is on the surface of Earth, then h equals 0, and the acceleration, as we know, is gravitational acceleration g on the surface is 9.8 meters per second square. So we know this one. So when h equals 0, we can replace the acceleration by 9.8 meters per second square. That is gravitational acceleration at the surface of Earth, right? So we have gravitational acceleration at the surface of Earth equals g mass of Earth divided by the radius of Earth squared. Okay, so that gives you the mass of Earth is gravitational acceleration times the radius squared divided by gravitational constant. Okay, so you see, to determine the mass of Earth, all you need is gravitational acceleration at the surface of Earth, which is 9.8 meters per second square, which can be measured, and the radius of Earth can easily be measured by measuring the circumference of the Earth, maybe by flying a plane around the world. You can measure it very easily. So that way you can measure the mass of Earth very easily. That's how they do it when they talk about the mass of Earth. All right. Now let's look at about objects in orbit. Objects revolving in orbit. Okay. So let's say we have this big object over here. Let's put by capital M, and then we have an object in orbit. Okay, an object that we have this mass M over here, moving in orbit, the circular orbit over here. Okay, so we want to get an expression for the velocity of this object in orbit. All right, so the force responsible for an object in orbit around this mass is gravitational force. Okay, of course, what makes this move in a circular path is centripetal force. In this case, the centripetal force is gravitational force. Okay, so the centripetal force for this motion in a circular orbit is provided by gravitational force, by the gravitational force exerted by M on M, right? So the centripetal force that's causing this motion equals the gravitational force. Okay, now since the force is radial, perpendicular to the tangent line over here, this force doesn't have a tangential component, so we expect the velocity to be a constant because this force doesn't have a tangential component. Okay, but we know that the expression for centripetal force is mass times speed squared divided by the radius. Okay, this is the radius. All right, mv squared divided by r. Therefore, this gravitational force should be equal to this centripetal force, which is basically mass times acceleration. So we have Fg, which is g small m capital M divided by the square of the distance, equals mass times speed squared divided by the radius. Okay, so you see this cancels out. This cancels out with one of this. Okay, so you've got v squared equals gm divided by r. So the speed by which the object in orbit is rotating is given by square root of gravitational constant times the mass around which it's rotating divided by the distance between the center and the location of the object. So this is the speed of an object in an orbit at a distance r from the center of M. This is speed of an object in an orbit revolving on a circular path with radius r, and a circular path with radius r. Okay. Next we're going to look at Kepler's laws. Kepler's laws. Kepler's laws are laws based on experimental findings. A scientist by the name Brahe spent all his life collecting data about the planets, and this scientist Kepler came up with 3 laws by studying these data. So we're going to look at these 3 data. Number 1, he said the shape of the path of the planets around the sun is elliptical. He said the trajectory of the paths of the planets around the sun is elliptical, or is an ellipse. Is elliptical. It has an elliptic shape. It's an ellipse. Okay. But for practical purposes, they could be approximated by circular paths. But for most of the planets, it can be approximated by a circular path. Okay, so the shape of the trajectory of the motion of the planets around the sun is elliptical. Okay, as you know, an ellipse has got 2 foci over here, so maybe it's longer in one side. This could be something like this. Okay, so the sun will be at one of the foci, and the planets will be moving in an elliptic path where the sun is located at one of the foci of the ellipse. Okay, so that is one of his postulates. The shape of the paths of the planets around the sun is elliptical, or the shape is an ellipse. Okay, the second one, he says the planets cover equal areas in equal intervals of time. So let's say you have this ellipse over here, let's say it's the sun over here. If you take this area in a certain time interval, and then once somewhere over here in the same time interval, if you compare these 2 areas, they would be equal if they're covered in equal interval of time. Okay, so the areas covered in equal intervals of time are equal. Okay, now this finding was obtained experimentally. It was deduced from the data obtained from the plants, but today we can actually derive it because we know what the gravitational force looks like. Now, it basically has to do with the fact that angular momentum is conserved for central forces. This can be proved can be proved easily from the fact that the gravitational force is a central force. Gravitational force is a central force, which means it depends on the distance between the sun and the planet. So now, for a central force field, the torque is 0. For the central force field, for a central force field, torque is 0. We can easily calculate, determine this. Torque is, if you remember, R cross the force. In this case, R cross the gravitational force. But the gravitational force is, let's say, negative G, the mass of the object, let's say the mass of the sun, and then you've got R divided by R cubed, okay? So the torque would be R crossed with this, negative G, capital M over R cubed, and then you've got position vector over here. So we can take this out. So this equals negative G M, the mass of the sun, divided by R cubed, and then R cross R, okay? But as you remember, if you cross a vector by itself, it is 0, okay? So the torque is 0. For a central force field like gravitational force, the torque is 0. But this implies angular momentum is conserved, okay? You remember, torque equals the rate of change of angular momentum with respect to time, that equals 0, and that implies the angular momentum is a constant. All right? So from this, we can actually calculate that the areas covered in equal intervals of time are equal. So what is angular momentum? Angular momentum is R crossed with linear momentum, okay? Or R crossed with mass, and velocity is derivative of position vector with respect to time, okay? So we can write as mass, and then we have R crossed by dr divided by dt, okay? But what does this represent? Let's say we have this ellipse over here, and let's say the sun is over here. So this is R, and dr would be this one over here, okay? So this is the area of this parallelogram, okay, which is half of the area covered in the time interval dt. That's what we're looking at, okay? So this one actually is twice this area over here. This is the area of this parallelogram over here, and this area covered time interval dt is half of this one. So this tells you, first let's look at the magnitude. That's mass, magnitude of R cross dr by dt, okay? But R cross dr equals twice the area, okay? So you have this angular momentum over here is mass times twice the area by dt, okay? So this tells you this dA by dt is angular momentum times the mass, twice divided by twice the mass, is a constant, okay? So that's it. This implies dA by dt is a constant, which implies the areas covered in equal intervals of time are equal, okay? That is, we've got dA1 over dt equals dA2 over dt. That implies dA1 equals dA2. So the areas covered in equal intervals of time are equal. So that proves Kepler's second law, that the planets cover equal areas in, or sweep equal areas in equal intervals of time. The third one The third one says that the square of the periods of the planets is proportional to the cube of their distances from the Earth. This states that the period of the planets, the period again is T, of the planets, I should say the square of the period. Let me write it again. The square of the period, the square of the period of the planets, is proportional to the cube of their distances, from the sun, okay? And this was obtained empirically from the data obtained by Brahe, but today we can actually prove it very easily because we have a formula for the gravitational force. So let's try to show it using the formula for gravitational force. Now, as I said before, even though the paths are elliptical, the path could be approximated to be a circular path for a number of the planets, okay? So we're going to assume a circular path, and so this is R over here, okay? So the centripetal force is provided by gravitational force, okay? So centripetal force is m speed squared divided by the radius, and the gravitational force is g m, the mass of the sun, divided by the distance squared, okay? Now if you remember, the speed is circumference to pi r divided by the period, okay? So if you do that, first let's simplify this, and we can take this one too, this one over here. So v equals circumference divided by the period squared equals g times the mass of the sun, and then we have r over here. All right, so let's cross multiply. So you've got g ms times the square of the period equals 4 pi squared, and then we r squared times r cubed over here, okay? So that tells you the ratio between the square of the period and the cube of the distance is 4 pi squared over g times mass of the sun, but this is a constant, okay? You can calculate this number, we know all these numbers, but this is a constant, and so if it's a constant, it implies that the square of the period is actually proportional to the cube of the radius. So that is the proof, okay? So the square of the period is proportional to the cube of the distance. So what this means, for two different planets, this ratio is a constant, okay? So this is, this t squared over r cubed is a constant for all of the planets, is a constant for all of the planets, okay? So for planet 1 and planet 2, planet 1 and 2, we can write t1 squared divided by r1 cubed equals t2 squared divided by r2 cubed, okay? So since we know the period of Earth, okay, which is 365 days, and we know this distances too, for all the planets, you calculate the period for the other planet using this formula.